Hello. I have quite a cool video today, but I realized that in the last video I actually forgot to play my intro. So we're just going to have to play it twice. What the heck? Quickly. What the heck? In the last couple videos I did a series over the zeta function at different integer values, or integer arguments I should say, that added up to the Euler-Mascheroni constant. And I did another one that was also a series over integer inputs of the zeta function that was equal to 1 minus the Euler-Mascheroni constant. So what I want to do is I want to combine those two things together because they were rather similar series that gave rise to rather similar results. And so when you combine them together, you actually get a very, very cool other series that we're not really sure what it's equal to, but I'm going to show what it's equal to in this video. And we're actually going to answer a broader, more general question that's very, very interesting and not obvious that one would want to ask this question about the harmonic numbers. And it's very, very cool. I've never seen this anywhere else. So let's dig in. So before we start the investigation of these series, we have to recall what the two series are. So the first one that we're going to consider is the one that's equal to 1 minus the Euler-Mascheroni constant. And this one was 1 minus the Euler-Mascheroni constant is equal to the sum from k equals 2 to infinity of zeta of k minus 1 all over k. And we were also able to show that the Euler-Mascheroni constant is equal to the sum from k equals 2 to infinity of negative 1 to the power of k times zeta of k all over k. And these are both very, very beautiful series, but the cool part is when you decide to add them together. Because look what happens. Negative Euler-Mascheroni plus positive Euler-Mascheroni is 0, and so the left-hand side is just equal to 1, which is very, very nice. And then we can combine these two sums together quite easily because they have the same indices. And not to mention that each respective term has the same diameter, so it's very, very convenient to combine these two things together. We have the sum from k equals 2 to infinity of, and I'm just going to combine the two numerators. So we have zeta of k minus 1 plus negative 1 to the k times zeta of k. And this is all over k, right? Because the same, I keep wanting to say diameter. Denominator, right? We have another simplification that we can make. We have two terms that have the common factor of zeta of k. So what I'm going to do is I'm going to simply factor that out of those two terms and have as sort of a product of two things. So we have the sum from k equals 2 to infinity of zeta of k, so I factored that out, times 1 plus negative 1 to the k. And this is still all, we still have to subtract this 1 right here, right? Minus 1. Ooh, that's just off the board. So there's a minus 1 right there. Minus 1 all over k. So this is our series now. So we have a very, very interesting setup going on here. So let's just read it out. We have the sum from k equals 2 to infinity of zeta of k times the quantity 1 plus negative 1 to the k, all minus 1 and all over k. The thing is, it's very awkward to have this alternating term be equal to 2 or 0, right? Because when k is even, negative 1 to the k is going to be 1, so we get 1 plus 1, which is 2. But when k is odd, negative 1 to the k will be 0, and we'll get 1 minus 1, which is 0. So what we're going to do is we're going to do a rather clever trick, actually. What we're going to do is we're going to leave the 1 on the left-hand side alone, but we're going to replace the top index of this sum with n, and we're going to do it as a limit as n goes to infinity. So the limit as n goes to infinity of this sum, this series, but now we're going from k equals 2 to n. And what I'm actually going to do is I'm going to take this part, the negative 1 over k, and write it as its own series, but separate. Because now, we know that if we summed from k equals 2 to infinity of negative 1 over k, that would diverge, because it's actually just a weird version of the harmonic numbers, you can quite easily see. But if we're stopping the index at n, then it's always a finite sum, and it doesn't actually matter. So the first term is going to be zeta of k times 1 plus negative 1 to the k all over k. That's the first term, right? And then the next one is going to be plus the sum from k equals 2 to infinity of minus 1 over k, right? Because we know that we've got minus 1 right there. And I didn't mean for that to be infinity, sorry, that's still n, and this is, the limit is applying to that entire thing right there. All we've done is replaced the upper index from infinity to n and letting n go to infinity, so it's written as a limit. And the point of doing that is now I can manipulate these two series individually, because if I let n go to infinity, they would diverge and it would cause a problem. So I have to sort of manipulate them in the finite world first. And what we're actually going to do now is another quite clever trick, in my opinion, is we're going to consider the fact that this term, 1 plus negative 1 to the k, is 0 whenever k is odd, and it is 2 whenever k is even. So we should exclude all of the cases where k is odd so that we only consider the terms that aren't 0, right? So what we want to do is we want to plug in 2k for k, right? So this is going to be equal to the limit as n approaches infinity, this is still equal to 1, of the sum from, I'm not going to plug in the indices yet, but we're going to have zeta of 2k times 1. Now what's negative 1 to the 2k? Negative 1 to the 2k is 1, because 2k is an even integer, which means we're raising negative 1 to the power of an even integer, which makes that equal to 1. And we're going to get 1 plus 1, which is 2. So I'm just going to write a 2 right there. And all divided by 2k. Right? Because we're plugging in 2k for k. But if we're going to plug in 2k for wherever we see a k, that means our indices have to be divided by 2 so that the sum is still equal to the original sum and we're not actually changing its value. So all we have to do is change k equals 2 to k equals 1, because that's 2 over 2, and change n to n over 2. Okay? So that may seem a little bit odd to have, you know, like a fraction as an index of a sum, which has discrete terms defined by integers. But as n goes to infinity, it's not really going to matter whether or not n is even or odd, because you're going to keep collecting all of these terms that are just going to get more and more accurate as the sum gets higher and higher. And so what we're going to do now is we're going to remove some of this harmonic-looking series over here and move it over to this side of the equation. And we're actually going to move this term back over. Well, look what happens if I subtract 1 from both sides, first of all. So I'm making this side 0 now. If I subtract 1, I'm going to get this sum here, which is k equals 2 to n of negative 1 over k. If I subtract 1 over, that's like having negative 1, which is actually just the k equals 1 term of this series. So we can actually fill that in as though we were missing it all along. So now we can start this at k equals 1 to n of negative 1 over k. Right? But we can't really meaningfully combine these two series unless they have the same indices, right? So this one goes from 1 to n over 2, and this one goes from 1 to n. So if we take all the terms here that go from n over 2 plus 1 all the way up to n, then we'll be left with a series on this side of the equation that has the same indices as that one. If that's not completely clear, hopefully you'll see it when I do it now. So I'm going to distribute this negative into here. So I'm going to distribute the negative out there so that when I add it over I get a positive amount. So I'm going to take all the terms of this series that go from k equals n over 2 plus 1. So now I actually have to put the limit as n goes to infinity on this side, as n goes to infinity, of the series as k goes from n over 2 plus 1, right? Because we want to start at the term after n over 2, right? So n over 2 plus 1 all the way up to n of 1 over k. And so I've just taken that part of this series and moved it to the left-hand side of the equation. And so we still have the rest of the stuff over here. So we have the limit as n goes to infinity of the series from k equals 1 to n over 2 of zeta of 2k. And now this 2 and that 2 in the denominator and numerator can cancel, so we're just going to get zeta of 2k divided by k. And because now we're just going to be left with this same series, but only up to n over 2, they'll have the same indices now, and so we can just combine the two things together. So because this one actually has a denominator of k, 2 divided by 2 is 1, and so does this one, we can just combine them together in that way. So we get this series to end, but now notice the only thing that depends on n on the right-hand side of the equation is the index of the sum. So we can just let n go to infinity, right? And we know that at every step of the way, this has been like legitimate movements of things around. We're about to encounter a bit of an issue here, so we might have a bit of a problem with what I'm about to say. But so we're literally just going to let k go to n go to infinity. So we get the sum from k equals 1 to infinity of zeta of 2k minus 1 all over k. Now this is a very exotic looking sum. I'm not sure that I know that it does in fact converge, but as part of this video, spoiler alert, we don't know that this converges or not, right? This limit this limit of summing from the harmonic numbers from n over 2 plus 1 to n, like the reciprocals of the integers, we don't know that that necessarily converges. We can actually write it in a cool way though, that is going to help us find it out, because we can answer a more general question to answer this question here. But first we need to see that this is actually of a pretty nice form. So this is equal to the limit as n goes to infinity of, now what we can do, because what we did was subtract part of this series to the other side, we should actually write it as those two separate pieces, because what it is really the sum from k equals 1 to n of 1 over k minus the sum from k equals 1 to n over 2 of 1 over k, which is to say that this limit is equal to the limit as n goes to infinity of the nth harmonic number minus the n over 2 harmonic number. And so this is a very, very neat way of expressing this, but this, if this limit exists, then it is equal to this series right here, right, that we just derived. The sum from k equals 1 to infinity of the quantity zeta of 2k minus 1 all over k. So if this limit exists, it's equal to this series. So what we're going to do is we're actually going to answer a more general question than this, which will actually give us the answer to a more general form of this expression, which will, in the specific case of 2, we get the answer for this series here. So let's answer that question. Let's take a look at a more general version of this problem here. So I hope everything was clear up till now. All we've done is taken two series that we've derived previously and manipulated them to come upon another series that we first have to prove, that is another series that is equal to a limit that we first have to prove converges to a specific value, and that would be the answer of this series. But we're going to answer a more general question first to sort of attack the problem in a cooler way, I would say. So we're not going to ask about the nth harmonic number minus the n over 2 harmonic number. We're going to ask the more general question, the limit as n goes to infinity of h sub n, not minus h sub n over 2, but instead h sub n over k. So we're going to be answering the general question, we're going to think of this as a function of k. Right? N is going to infinity, so it's sort of being allowed to change. K is the fixed input of this function. We want to know if there's like a nice function that represents this difference here. And it turns out to be very, very neat. Notice that in the case of f of 2, we get our sum, right? From t equals 1 to infinity of zeta of 2t minus 1 over t, right? So f of 2, if it exists as a limit, is equal to this series. That's what we just derived. And so what we're going to do is we're going to do some fancy schmancy little manipulations of this limit. And because I'm pretty sure that even if limits of individual terms may diverge, if you break that limit up into pieces that themselves converge, even if individual ones don't, that still is valid limit manipulation. So if there's any issue with what I'm about to do, because I've never seen this anywhere before. This is something that completely came out of my own head. So what I'm going to do is do some manipulations of this limit to find out what f of k actually is. So what we're going to do is we're going to add and subtract the same thing on the inside of this limit. So we have the limit as n approaches infinity of h sub n, and I'm going to subtract the natural logarithm of n, and I'm going to re-add the natural logarithm of n. So we still have minus h sub n over k, and I'm going to add the natural logarithm of n. But instead, what I'm going to do now is I'm going to rewrite the natural logarithm of n as something different, slightly different. Because what I can do is write n as equal to n over k times k, right? That's perfectly fine, because k divided by k is 1, and I'll be left with the natural logarithm of n. But because this is a product inside the natural logarithm, I can write the natural logarithm as the sum of those two things. So this is equal to the limit as n approaches infinity of h sub n minus ln of n. And what I'm going to do is I'm going to write this as the sum of the two things, so the natural logarithm of n over k plus the natural logarithm of k. But then I'm going to factor out the negative 1 from here and the natural logarithm of n over k. So what I'm going to end up with is minus h sub n over k, and then this is the quantity, h sub n over k, and I'm going to be subtracting the natural logarithm of n over k. Because if you think about it, I have the positive natural logarithm of n over k here, and I'm factoring out a negative 1 from this term and that term. So the one that was negative becomes positive, and the one that was positive becomes negative. And so what I'll be left with on the outside here is plus natural logarithm of k. But if you'll notice, if I were to break this up into different limits, this limit would converge, this limit would converge, and this limit would converge. And look what happens. So this is the step that I'm not entirely sure is valid, but I know that the conclusion is correct. So I mean, this is sort of an Eulerian way of attacking this problem, where I'm not exactly sure that things are perfectly well defined and converge, but it. Because that's how cool math gets done. But I'm going to put a little question mark above my equal sign in case there is a problem here. So I'm breaking this expression up into 3 different limits. The limit as n approaches infinity of just the first 2 terms, h sub n minus ln of n, and that should have been sort of obvious what we were going to go with that. And then what we're going to do is we're going to subtract the next 2 terms as a limit. So the limit as n goes to infinity of h sub n over k minus the natural logarithm of n over k, plus the limit as n approaches infinity of the natural logarithm of k, right? So those are our 3 limits. But notice, the first limit is what started this whole series off. This is the definition of the Euler-Mascheroni constant, right? It's the limiting difference of the nth harmonic number and the natural logarithm of n. So this is just the Euler-Mascheroni constant right here. Notice we are then subtracting the limit as n goes to infinity of n over k harmonic number minus the natural logarithm of n over k. No matter what number k is, because it's just some number, right? No matter what we're dividing it by, this n getting bigger and bigger will cause both of these terms to go to infinity. So the limiting difference is still the same. This is minus the Euler-Mascheroni constant. And then we're left with the limit as n approaches infinity of the natural logarithm of k. Well, the natural logarithm of k doesn't depend on n whatsoever, so this limit is irrelevant. It's just ln of k. And notice the Euler-Mascheroni constants cancel, and we are simply left with ln of k. The function, this limit that we started with from the beginning, here, is really just the natural logarithm of k, which is an amazingly simple result to get. If you take off every term from 1 to n over k in the harmonic series, and then you take that away from the nth harmonic number, and then let n go to infinity, you end up with the natural logarithm of k. What does that tell us? What does that tell us, though? I'm getting all excited. That tells us that our function, our series, from k equals 1 to infinity of zeta of 2k minus 1 over 2, which we know it to be equal to f of 2, is just equal to the natural logarithm of 2. That's an amazing result. That's truly awesome, right? Like, I mean, we've been able to pull 1 out of this. We've been able to pull the Euler-Mascheroni constant out of these. We've been able to pull the natural logarithm of 2 out of these. We'll probably be able to come up with series where e or pi are involved with the Riemann Zeta function. It's just such a versatile function to do series studies with, which is why I'm really going to get into like rational zeta series in not too long, because I think the study of those is really interesting. So we have a very, very cool result here. That this series that we got from combining 2 other ones that gave us the Euler-Mascheroni constant is actually just equal to the natural logarithm of 2, which, if you're not entirely sure, is about 0.693, I believe. I really need to clean this board. That's really hard to see there. This is like from me having coffee at my board. It's a bit of a stain. Quick little thing, this channel has an Instagram, so it is at whatthehectagon, of course, and it has a Twitter, and it is of course naturally, also at whatthehectagon, and my email is the incorrectly spelled whatthehectagon, why spell check before you make the email right, that you can't then change, at gmail.com. Now, all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. That's the stuff. Thank you for watching, and bye-bye.